Hi, Professor.
Hey, how are we doing?
Good, how are you?
Are there any questions here before we get started?
Um, so I saw that you posted, the homework 7 and 8 solutions, and you wrote that homework 10 is going to be prorated.
Yep.
So will you post the homework 9 and 10 solutions this weekend after 10 is due?
Yeah, and so
Okay.
if I forget to do that, can you just send me an email Sunday morning and
Yes.
I'll get it done? Okay.
Yes. Okay. Thank you. Just wanted to confirm.
Yep. Okay, guys. This is the last lecture. Um, so before we get started, there are two practical things that I want to talk to you guys about. So one is these online evaluations. Please, Phil. Please fill yours out. The other thing is there've been a couple of students in this class and also a couple of students in the other section of 45 that have asked about 486. And so I've been trying to think about what such a course could look like. And so I am seeking your input to that. And I came up with the following. So there'll be so this year is going to be for future editions. I am not sure when it's going to run, but at least tentatively, the goal is to have it run not this spring, but the spring of 2022. I don't know about the spring of 2021. This is unclear. The components that I had in here was so academically, right? There are more advanced models. We talked a little bit about some of them, but there could be stuff on fixed income. There could be stuff like Americans. There could be stuff like jump processes. And there could be stuff like default models. There are lots of topics that we could include. So that's one part of it. The other part, there are two other components to it that I wanted to get your opinion about. So the other one would be, so we would start doing homework, but we would have a computer component. So with like you have a computer implementation of these standard models. Like we already talked about Heston, we already talked about Vesicek, and so on. Right, so there'll be something here about calibration to data. So this would be so the first one here would be the first item would be a direct continuation of what we've been doing. The second one here, this will be different, right? We haven't done computer implementation in this course. And then the last one, some of you asked a few times ago about presentation. And so the last one would be like a capstone project. A capstone project with a like a final all slide presentation. Right, so instead of having exams, instead of having finals, what we would do is we would have a large homework towards the end, and then there will be this element of getting some experience on how to actually do a slide presentation. Most of you will at some point in your career need to do that. Right, so these are some thoughts on 486, and I just wanted to see, since you guys, it might not be available in the spring. I doubt it's going to be, I doubt it, but it might be available down the road. So I wanted to see what you guys' opinion was, if this was something that some of you might be interested in, or if you had any comments on a proposal that would include like A, B, and C.
Professor, there is a course already called 486, and it's a different course.
Okay, so we'll call it 45 plus.
Yeah.
I made a poll, so we can try to do that and see what you guys think. There are 14 students here. So we are 14 students, and it splits somewhat half and half between. So there are 5 up here, 1 here, and 7 here. So there is the goal, I think the department would have is about 10 students. So you have to pick up some of the 7 down here, plus some of the 5 here, and then some from the other section. Okay, these were all the practical things that I had. Other than that, my plan for tonight would be to see if there are questions or comments that you guys want to try to square away about some of the material that we've been covering here in the last few nights. We can. I have a couple of problems in mind that we could start by, and then maybe we can get some questions or comments going. So let me start by sharing the set of problems. The problem I had in mind was, so we were talking a little bit about 6 last time. So the next one is number 7. So again, number 7 is one of these models that have, it has 2 Brownian motions. And then there's this V process, which is familiar to us. This is the square root process that we used in earlier lectures. And you can see here that the model has a stochastic interest rate. Right, so the interest rate is this VT up here. Then there's a stock, and you can see the stock has a drift and it has a volatility. So the first question is, solve this SDE for S. We can also solve the SDE for S0. Then it comes into Markovian. Then it comes into, is it arbitrage free? And then it comes down to hedging and pricing. So this is a problem that will take you through basically all the elements that that we talked about in the last few weeks. So I want to see how it will go on a problem like this one. So this here is number 7, an old exam question given out some years ago. So we have 2 Brownian motions, B and W, and they're always independent. They're always such that the cross variation between them is equal to 0. Right. So we're looking at the bank. This is our S0. So it has this. It has this form. Our bank starts out at 1. Now V here is by itself a stochastic process. So V here has dynamics on its own. So it has this affine drift. And then it has this square root structure for the volatility. So here comes the first Brownian motion. And here comes the second Brownian motion. And as we talked about last time, what we have inside here, so it starts out somewhat positive. What we have inside here, this is a, we would call that for, say, Y. And then Y is another Brownian motion. Okay, so, so this is the bank, and this is the interest rate. V is this stochastic process here. So there's a model that has stochastic interest rates. The first question is, try to solve for S0. So S0 here, this is an ODE because there's no Brownian motion over here. This is just an ODE. And if we have an ODE of the form f prime equals f times something, I'm hoping at this point we're comfortable saying that, well, ST0 is equal to the initial value and then an exponential of VU du. Right, you can just check this. You just compute the derivative with respect to t of ST0. Then you will get the derivative of an exponential, that's the exponential itself, times the derivative of what's inside. The derivative of this integral with respect to its upper limit is going to be Vt. So that's what you have up here. D, you move the dt over to the other side, and you get exactly what's on the right hand side. Any questions on this part? Then comes the stock. So this was the bank, and now comes the stock. The stock has dynamics. dst is equal to st, and then it has a drift. Mu is a constant. V is the process up here. dt plus, then it has a volatility. The volatility is the square root, and then there's only dbt. And it starts out somewhere positive. So just as just as we solved the equation that describes the price of the bank, likewise, we're going to solve the equation that describes the stock price, right? You have S on the right-hand side, you have S on the left-hand side. So now the big difference is that up here, you just have a dt, and down here, you have a dt and a dB. Right, so now this is not going to be the case anymore. There's a Brownian motion that's going to mess things up. And so to fix this, you need to use Ito's lemma. So how do we use Ito's lemma? Well, we could start by saying that what we have in here, let's give this a symbol. We call this for x, so maybe we can call this for y, maybe we can call this here for x. So if we call it xt, right, then what is the solution to an equation like this one? Can we write this here as st is equal to something? Well, what we could be is we could try to mimic this exponential, and then we could put xt here. But because there's Brownian motion over here, we have to be careful. We know that there's going to be something with a half and then quadratic variation of x. Like in the dynamics of the quadratic variation, we get that from squaring the volatility and then quadratic variation of Brownian motion. This is dt. So maybe we could come up with a guess like this one, and then we could check it. So let's check the guess. Check the guess using Ito. Check the guess using Ito's lemma. So how would we do that? Well, we will recognize that this here is a function. This here is a function of xt minus 1/2 quadratic variation of xt, where the function is just the exponential. F of a is e to the a. So when we use Ito's lemma, we can compute ds simply by computing d of f of xt minus 1/2 quadratic variation of xt. Right, so this here is my process, and this is my function. The function is an exponential, so whenever I compute derivatives, I will always just get the function back. I need to compute two derivatives, and I'll always just get the function back because it's the exponential function. So when I use Ito's lemma, right, so it's Ito's lemma is going to make, Ito's lemma is what's going to come in the next equality. Ito's lemma is going to come here. Ito's lemma says that you have to compute f prime, and then you take this thing. So this is f prime evaluated at xt minus 1/2 x, quadratic variation, and then you need d of this thing, xt minus 1/2 quadratic variation of x. That was the first term. And then the second term, this is where we get 1/2. And then you need f double prime evaluated at xt minus 1/2 quadratic variation of xt. And then the quadratic variation. So I will take the quadratic variation of this object here. This will be x minus 1/2 x t. Now we'll insert the derivative of f. That was f itself. Okay, so I'll get f back here. This is f of xt minus 1/2 quadratic variation of x. And you can see that this is going to be the same for both of them. So I'll put a curly bracket here. And then what will I do? I'll need to know now what the credit gradation is, and I'll need to know what dx is. So I'll plug those in. Dx is up here. This is mu v dt plus square root vt dbt. That was my dx minus, and then I have 1/2 the credit gradation. This was vt dt. So that was the first part. Right. This component here, this is dxt minus 1/2 credit gradation of x. And then we also need the other term, get plus 1/2. If double prime goes outside, and then I need the dynamics of the credit gradation of x minus 1/2 is credit gradation. So the credit gradation of x just has a dt term, so I can forget about him. I'll just get here the credit gradation of x, which is v dt. Right, this part here, this is d of x, which is equal to d of x minus 1/2 credit gradation of x. And now we can see stuff cancels out. You can see that the plus 1/2 v here cancels out the minus 1/2 v here, and you're ending up with f of xt minus 1/2 credit gradation of xt mu vt dt plus square root vt dbt. Right, and this here is exactly dxt. So there you have it. This function applied to x, it solves the SDE that we're interested in. It solves this ds is equal to sdx. Here we have my function. The function comes back, and then dx. Right, so it shows really that, so it is really true that x st is equal to e, and then x was, I have dx, so to get x I need to integrate, integral from 0 to t of mu vu du plus another integral of square root vu dbu. That was the first part, and then I need minus 1/2 the credit gradation. That was this guy, integrated vu du. And then we need the initial value over here, S0. So I should have an S0 here. So that's my solution, and you can see it's different. You can see it's different. If I just had a dt term up here, you just get an integral with respect to time, respect to du. But if I have a Brownian motion term, like this one, I will not just get the thing integrated, I will have to correct it with this minus 1/2 of this credit gradation of the first, of the Brownian motion term. So that's why stochastic calculus in this way is a bit different than ordinary calculus.
Professor.
Yeah.
Quick question about me. Remember you for the interest stochastic process? Yeah. When we took the partial derivative. Yeah. Excuse me. Why did the e the exponential, it looks like it disappeared to me for some reason.
No, it's right in here.
Where is it?
This part here, right? This is the integral from 0 to t of vu du.
Oh, you substituted it in already. Okay, I got you. I see.
Other questions? This was the first part of question 7. So let's move on to the next one. This is about macro processes. This is something we talked about a little bit. So which families are Markov? We started out with B and W. Is B and W Markov? Yeah, that's okay. Brownian motion is Markovian. We proved that. That's been a while. We proved that early on. Then the next one is VT. Is VT Markovian? Well, there the thing to look for is it true that the right-hand side's coefficients are just functions of VT? So what we need to check is, so we need to check if VT's drift and vol are functions of VT. Right, so VT's drift is affine, right? This was this kappa theta minus VT. So is that just a function of VT? Yes, this is okay. And then VT's vol, this was beta root VT times a rho. This was the dBT term. That one, yes, this is okay. This is a function of V. And then the other vol term was VT, and then it was square root 1 minus rho squared. This here was the dW term. Is that also just a function of, V? And yeah, it is. This is also okay. So when you can check that off, then VT is a Markov.
Does it not the Brownian motion, the dynamics of the Brownian motion?
Yeah.
That doesn't it's not a function, not another function that we need to consider, only the DT.
In the first part or in the second part?
In the second part.
Now you're confusing me. Which one? So we have drift, and then there's the first vol term and the second vol term.
Yeah, so I guess what I'm saying is like, how do you, so the dBT isn't a function.
No, you just have to look at the coefficient.
Oh, okay.
You're right. You have to look at, check if VT's drift and vol are functions. So those are the coefficients. These here are coefficients. Maybe it would be clear if you looked at S. So let's look at ST. Right, so this here was one question, then the next question is, what about ST? Well, ST was given here. ST was given here. So now we look at ST's drift. The drift was ST mu VT, and the vol, this was ST root VT. This was the dBT term. This one here was the DT term. Is this just a function of ST?
What about that VT? Is that a different thing?
Can you say that again, Richard?
What about the VT? The VT, is that a the VT?
That's the problem, right?
Yeah. So that's a
no, and this is a no. So this is not Markov.
why do we only have to look at the coefficient again? Sorry,
Yeah, so that's
I'm not understanding this.
so this is the way to check for Markovian. We talked just a little bit about that at some point, but we haven't specified all the glory details that we need for this. But this is the way that one will go about figuring out if a given stochastic process is Markovian. What you do is you look at the volatility and you look at the drifts. Are these objects just functions of that process itself, or do you need more information? And here it's insufficient just to have S, because you also need to know what V is to determine what the drift is and to determine what the volatility is. So if I wanted this Markov property, and this is the last question, it says, what about if I paired it up? So I looked at VT and ST. Well, then I would have drift. The drift would be, well, it would be kappa theta minus VT. And then the other one would be ST mu VT. This here is VT's DT term. And this one here, this is ST's DT term. Are these two terms are these functions of V and ST? And now this is okay. And likewise, say again?
So it doesn't have to have both?
It can have, right? This here is a function. This is also a function of S. It's just a constant seen as a function of S.
Okay, I see.
The problem is that this thing here, this is not constant as a function of V, right? Because V is sitting out here. Indeed, it's linear and it's a square root. And then you look at the balls. If I look at the ball of V, then I need two terms. So this is VT's, we have two terms. So this the BT term. That was the beta root BT rho. And then we had the other one. This was ST root V. This here was ST's dBT term. Are they both functions of V as well as S? We have a look. Yeah, there's V here, S and V. You're okay. And then finally, the second vol term we have to check out is, well, I look at VT's dW term. Then there I'll have beta root V root 1 minus rho squared. And ST doesn't have such a term. Right, so this will be a 0. Are they all functions of VT and ST? And they're okay. Right, so then VT and ST is Markov. I said where it becomes important is, so this is important for computing. For computing, for example, if you were to compute an expectation of a function of, say, ST, given, say, Fs. Right, so you take a function, I want to compute a conditional expectation. Now, what should this here be? Well, we want to conjecture this is like a function of, well, it'll be a function of S. And then what else would it be a function of? Well, this is where the Markov structure becomes important. Like, how many things do we need to keep track of? Well, if I have a function here of ST, I should keep track of S's current value. But is that enough? And the answer is no, this is insufficient because S by itself is not Markov. So you need to have more things in here than just S, and indeed what you need is to go up and include V. So is S and V then Markov? And then the answer is yes, you're Markov.
What was the little s there stand for? Oh, it's the time.
That's just time, right? It's just T here is bigger than S. And this is in contrast to if you were to compute a function of, say, Vt. Let me put a U here now so you don't get it confused. So now T is bigger than U. Well, this is again going to be a function of current time. This is U, and then V. But will you need more in here? Well, it depends. Is V Markov? And then you go back up and check. Is it Markov? Markov, Markov. Okay, okay, we're good. Then that's it. So you can see, because S is not Markov by itself, you need to go up one dimension. Here, V is Markov by itself, and then you just stick with one dimension. Any questions about this part? The third component to this question is more along the lines that we did last time. So let's do that again. We need to find equivalent martingale measures. So this is number 3. We need to find equivalent martingale measures. So this is where we need to start looking at the filtration. So our filtration, let me just recall, is the one generated by 2 Brownian motions, B and W. Right, so right from the beginning, how many market prices of risk do we have?
2.
2. And I won't call it theta because this theta is already being used for something else. Let me call it lambda, lambda BT and lambda WT. Okay, so we're going to be looking for, Radon-Nikodym derivative processes, dCt of the form minus CT, and then the 2 market prices of risk. Oh, this is a W. So we're going to be looking for these 2, such that something happened, right? Such that we're going to be looking for Radon-Nikodym derivative processes of this form. You start out at 1, such that when I'm looking at Q on a set A, satisfying the property that CT is the Radon-Nikodym derivative with respect to P on any set in FT, such that this measure, such that under Q with this property, we will have that ST divided by the bank is a martingale. So what we need there is,
Professor, so I'm just trying to understand this part. So we want to create the Radon-Nikodym derivative process that in that equation you wrote, and we want that to satisfy this integral right here.
so you're going to create the 2 processes, right? And then you're going to create the measure. So now you know what, as soon as you tell me what these 2 processes are, you told me what CT is, right?
Okay.
And then you're going to get your Q, right? So given these CTs, you're going to get a Q out to satisfy this. And then you want this measure to be such that this is a martingale under Q.
where was the? So we're trying to answer, is the model arbitrage free?
Yes.
Right. This is the question. Okay.
Right, and this is going to be arbitrage free if you can find such a measure Q.
I got you. Okay. Okay. I see.
Yeah. Whenever people ask you, that will be me in a few days. If I ask you if the model is arbitrage free, you have to create these meshes. This is the way to do it.
So I have another. So remember that we have like change of. Is this the same? Is this a does this a change of measure? What's happening here?
Yeah.
Okay. Okay.
Right. You move from P to Q.
All right.
Okay. Right. B and W, they are P Brownian motions. These guys are P Brownian motions, right? And this ratio here is not going to be a P martingale. Indeed, if you work out what the dynamics are, d of st over st0, but this is going to be, I know what st0 is because we did that in the beginning. This was d of this exponential integral from 0 to t minus vu du times st. Right. So here there's no Brownian motion. So when we apply the product rule, normally we get 3 terms, but we're only going to get 2 here because there's no Brownian motion in the first part. So when I compute d of this, what I do is e to the minus integral from 0 to t vu du, and then I'll have ds plus, and then I'll do the opposite, st d of e to the minus an integral from 0 to t of vu du. And then I should have cross variation here, plus the cross variation.
So we're using Ito's product rule here?
Yes.
Okay.
Ito's product rule, right? But this cross variation term, this is equal to 0. So we don't have to worry about that one. So let's work out what this here is. This here is equal to, you can see again that there'll be this exponential term that's common. So we can put him outside. And then you write. Now we need to plug in what ds is, which I don't really remember, but that was given in the assignment. We need to plug in what ds is. It's this long mess up here. ds was s mu v dt plus root v dbt. That was my ds. And then we get the second term. This is st d of this thing here. This is where the exponential comes outside, and then I get a minus vt dt. And what we want it to be is 0 dt plus something that has a plus something that is a martingale onto this measure q. So what we need is, well, we'll have the first term here, and then we have our s, and we have the root v. So then I need to know what happens to the Brownian motion when I move to a different measure. And that's where these market price of risk up here come into play, right? This thing is a correction term. This is the correction term that one needs to add in order to get a Brownian motion under the new measure. So here we will have to write here we'll have to write dBT plus, and then the market price of risk attached to B. This is what I want. Because this here is a Q Brownian motion. So I need this 0 here. And currently I have a dt term there, I have a dt term there, and then there's a correction term from down here. So there are a bunch of things that have to add up to 0. And so what are those terms that have to add up to 0? Well, what do I currently have inside the 0 here? I will have ST times mu V minus V. And then I've added something here that needs to be subtracted. So I need to have a minus here with root VT and then lambda T B. Right, I need this to be a 0. And I solve, I get this one is equal to mu Vt minus Vt divided by square root Vt. That's going to give me what this guy is, and the other one is free. There's no restriction on him. And the reason that there's no restriction on the second one is because when you look at the stock price dynamics, you see there's no DW anywhere.
I see. Can we go to the bottom of the last page where it was calculations? Yeah. So the cross variation was 0 because,
right, if I look at what's downstairs, right, this the cross variation that you need here. This is right, this term here, this is d of 1 over st0.
okay, and there's no Brownian motion in the equation for st0.
That's right.
So that's but but it's between, wait a second, it's a cross variation between 1 over st0 and st.
Yeah.
And but st has a Brownian motion.
Yeah, S has Brownian motion, but this one here does not.
So if one of them doesn't have a Brownian motion, then
Then it's 0.
just
Yeah.
0. Okay. All right. Now, all right. Okay, so when we went from the second equality to the third equality, right?
Yeah.
The dst, that was just a substitution.
Yes.
And then this part, I know we did like that partial derivative thing in the last problem, and it looks kind of similar to what happened here.
It's the same. There's just a minus sign, right? Because you're 1 over.
Right. But what I want to say? Like because I get a little confused when I had the D symbol. When the D symbol is in front, it was like it's like an integral.
Yes.
Right.
Yep. Right. So when I say d of e to the minus, right, so now this is a separate question here. We're claiming that this thing here is equal to, what was it? This was 1 over st0 times minus VT dt, right?
Hold on. Is that what it said on the other page?
Right, you have your ST here, ST is there, then you have the other two outside, and then you have minus V.
Wait a second. What happened to the ST0? The one over the ST0?
It's right here.
Well, but what about in the?
It's there.
Oh, right. I keep on forgetting that's the same thing as ST. Okay.
This is quite important, right? I mean, whether I write 1 over ST0 or I write this exponential, this is tomato.
Okay.
Right? This one we already settled.
Yeah, no, we solved it on the last page. It's just that I'm not used to converting in my brain. Yeah.
We need to get used to this because these things are the same, right? Just as it's the same thing whether I write ds like that or I write this long messy thing. I write this long messy thing that I have here. The meaning of these two objects is exactly the same. So whether I write one thing or write the other thing, this is all the same. Right, so what's the meaning of this thing here? Well, the sloppy way is you just move this dt over here. Right? And if you don't like that, well, then what's the meaning? The meaning is that you integrate from say 0 to t of this d e to the minus integral 0 to t vu du. Right, so what would you get here? This would be, so this would be maybe an s. Right, so what you get here would be e to the minus the integral 0 to t of vu du. This is equal to, and if you want to have another, if you want to start out here, then it's equal to, I need to subtract away m1, right? Because that's the initial value. And so what I'm saying here is that this is the same. This is the same as integrating. This is the same as integrating 1 over SU with a minus sign and then VU du. All right, so all this stuff here is saying is that this exponential is equal to well, 1 plus or minus an integral from 0 to t of 1 over SU VU du. And now you can take a derivative, right?
Hold on. Let me get all this down. I feel okay. So I'm still a bit lost on. Okay. So I got how so we went from the first equation to the second one, right?
So what is the meaning of this thing between my fingers? Well, you integrate the left-hand side, and then you get the same thing as when you integrate the right-hand side, right? So I integrate the left-hand side. I'm just going to get this thing minus the initial value. So if the initial value of the integral is 0, right, I evaluate this thing here. For t equal to 0, I'm going to get e of 0. I'm going to get a 1, right? So on one hand, this is what I get when I integrate the left-hand side. On the other hand, what I get when I integrate the left-hand side is this thing. Right, so I integrate this thing out. So these two things have to be the same.
Oh, sorry. I got you. Like the second one is just the treatment of the left-hand side, and you evaluated the integral. Okay.
Yeah.
And then we're looking at the right-hand side after we have this.
Yep. So then you led to this expression here. And what I'm saying is that if you compute the time derivative of this quantity, so d of e to the minus integral from 0 to t of vu du, this is going to be equal to minus 1 over st0 vt. Which is exactly,
okay. Hold on.
Which is exactly what you have up here if you just sloppy divided it over.
1 minus, okay, hold on. I think I'm almost seeing the light here. And then the last step, we take the derivative. Okay, okay, perfect, perfect. Yes. Great, great.
Okay, are there other questions?
Zero. Great. Thank you, Professor.
Oh, hang in there. I do not mean to come across as saying that this is easy. That this is not true. Right? This here is something that takes a while to get used to. And the way that we're doing like the last few weeks of class is based on, this is almost like a flipped classroom, right? Where we do problems, problem, 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 problem. And are there any other questions about this part? So the thing to note here is that you do not have uniqueness. One variable is free, you do not have uniqueness.
So it's not complete.
So it's not complete, yeah, so it's incomplete, right? So this, so what that means is that there are claims that you cannot replicate, right? So there are claims that you cannot write. So then what is the next question? Okay, so now we're specializing. We're going to move into a specific model, a specification of what we have here. We're specializing to the case when rho is equal to 1. We're specializing to the case when rho is equal to 1. This is in question number 4. So now we're going to do rho equal to 1. And you can see the thing that makes this different is that this second rounding motion here now disappears. So now the model is that we have a stock. So now we're writing down dynamics under Q. We have a stock. Oh, well, I should say. So what's the model? So it's ST VT dt. The stock. If I write down the stock dynamics under the risk neutral measure, I'm going to get the rate to be VT. And then the volatility was square root VT dBTQ. Like, remember what this thing here was. This was dBT plus my lambda TB dt. So now you can see that there is no, because rho is equal to 1, there's no W, because when I write out what the dynamics of dV is, I would get this kappa theta minus VT dt plus this, what was it? Beta square root VT dBT. And again, if I want to write, the risk neutral dynamics of V, but I have to do this correction here. I have to add lambda TB dt. Right, this is my dWT and now I have to be careful, right? Making a correction over here to, so I have a minus beta root VT lambda TB dt. And maybe we can just recall, can we recall here what lambda b was? There's a square root downstairs, and then there's a linear function upstairs. So here I'm going to be multiplying with square root, so the square roots cancel out. I'll get kappa theta minus VT minus a beta, and then I would have mu minus 1 VT. And then I'll have my Brownian motion under that measure Q. Right, so we note here that this drift here, this is not V. This here is not required. This is not equal to VT because VT is not traded. Right, the other ones, you have V here and V here in front of the DT terms. But because this is the value of a traded security, so I know when I discount buy it, the bank, I'm going to have a martingale. This one here is traded. When I discount buy it, I'm going to get a martingale. I discount buy the bank, I'm going to get 0 DTs in both of them. But I do not have a requirement here that VT divided by the bank is a martingale, right? So this is not traded. So VT over ST naught is not required. Good night, guys. Good night. It's not required to be Q martingale. V is the interest rate. It's not the price of anything. Only traded securities, when you discount them by the bank, are required to be martingales. Equivalently required to have the interest rate as the drift. Right, so this mess here, it doesn't have to be V.
Could you explain where like the row, you said something like the row equals 1 like makes the term disappear?
Yeah.
Really see
No, because you're not there.
Oh, okay.
You're not there.
We're not at the punchline yet.
We are what slide were you on? Here you go. Right here. This here was a general specification, right? And you see this W term. If you put rho equal to 1, this term here drops out.
Why? If you put row equal to 1?
Well, 1 squared is 1.
Oh, sorry. I thought that I couldn't read. I thought that was like so that thing is row in the.
This is rho and this is rho, right?
Okay, gotcha. I get it now. I got you now. Yeah.
So what we see here, so for example, we see that V, when I look at the drift of V, this is an affine function of V. And I look at the volatility, it's a square root of V, right? So in particular, V here is Markovian, also on the Q. It was Markovian on the P, it's also Markovian on the Q, because the drift and the volatility, those are both functions of V itself.
You called it a what function? An affine?
Affine?
Did you call it an affine function?
Yeah, this is an affine function of V, right? An affine function right, so we have right f of x equal to a plus bx. This is affine. Whereas f of x is equal to bx is linear.
Oh, does affine have to do with like I remember like affine transformation, where like if like there's like the matrix associated with the linear transformation is like.
Sure, you can have this as a vector, and you can have that this here is a matrix. This I wrote it down here like V is one-dimensional. So this is a one dimension. I mean, the domain of the function that I have written down is R. But you could write this down as, if you wanted a higher dimensional, then B has to be a matrix.
Gotcha.
Right? Affine functions, they look like that. Linear functions, they look like this. They go over to 0.
Got it. Okay, so affine just means there's a shift from
yep.
the
Affine functions typically the equal to a linear plus a constant, right? And this is exactly what you have here, right? V, this part is linear, but over here you have kappa theta. This is a constant. Right, so you have a linear function v plus a constant.
Yeah. Got it.
So the question asks us to look at zero coupon bonds. So this is again something that we have done, but it's been a while. So maybe it's a good idea to do it again. So we're going to price a zero coupon bond. Right, so the payoff is given to be $1 over here. Just use the same notation as in the problem. Right, so this here is the time capital T, and we're sitting here at time little t. So we want to compute the conditional expectation under the risk neutral measure of, we need to discount. So this is e to the minus an integral from, like I have $1 here. I want to know what the price is of this thing at time little t. So I discount the $1 back. The interest rate was V. My goal is to compute this quantity. This is the price of a zero coupon bond. And there's a hint that says that the hint is that compute functions such that it has this exponential affine form that we looked at before, a of t minus t plus b of t minus t times vt. So again, v is Markovian, right? So you only have to keep track of the current value of v. And your job is to find ODEs for a and b. Right, these are functions of time. Okay, so we start by, for example, putting little t equal to capital T. If I take t to be capital T, then the left-hand side becomes 1. The right-hand side becomes e to the a of 0 plus b of 0 times b capital T. So if I want this to be true, I should pick a0 and b0 to be, if I want this to be true, a and b should start out
0.
0. Right, and now we're interested in what happens when you're less than t. But this is the harder one. So this is where martingales come in. So this object here on the left-hand side is not a martingale, right? Because we have a t here, and we have a t here. So we're going to look for a martingale. So we're going to note what? If I multiply through here with e to the, what should I do? Minus 0 to t of vu du times this conditional expectation, a t minus t plus b t minus t vt. This is a Q martingale, right? Because it's equal to the conditional expectation of e to the minus an integral from 0 to t of vu du given ft. And this is a Levy martingale. The little t is now gone. Conditional expectation of a random variable. This is going to give me a martingale. So I know that this object here is a martingale. Okay, so then I'll just apply Ito's lemma, more specifically the product rule, and we should be good to go.
Wait, Professor, could you explain how you knew that was martingale?
Conditional expectation?
Yeah, this form that you wrote down, like the note, this is a Q martingale.
Well, I multiply this quantity here onto the left-hand side. and then onto the right-hand side.
Uh-huh.
So the left-hand side becomes that. The right-hand side becomes this. Right, so the equal.
Right, yes, yes.
And this here is a martingale.
Okay, I got you. So, so we knew before that that was a Levy martingale, and then we just manipulated it to look like
Yes,
that.
that's exactly what we did. That's exactly what we did. So now we apply Ito's lemma. This is a product. So you can use the product rule. We need to work out what this thing here is. So now this is a function of t and v. So to compute the dynamics of, I'll break it up into 2 steps. So let me compute d of this thing here first. D of e to the a t minus t plus b t minus t vt. This is where we use Ito's lemma. We need time derivatives, and then we need derivatives with respect to vt. Okay, we're going to get this exponential term over and over and over. So I'll put it outside parentheses. And here they come. So we start with the time derivatives. We're going to get time derivatives, you will get minus a prime t minus t. Minus b prime t minus t vt. dt, that was the first term we need to. Then we need a derivative with respect to v. That'll give me b t minus t dvt. And then because there's Brownian motion inside v, I need double derivative. So I'll get b for the first, I'll get b for the second, and then credit variation of v. Okay, so now we need to figure out what dv is and what the credit variation of v is. Okay, so we go up to the dynamics. We're computing expectations under Q. So I need the Q dynamics. So I need to make sure that I'm looking at something that has a Brownian motion under Q here, right? Do not use the P dynamics. Do not use the dynamics of V where you have a P Brownian motion. If you're computing expectations under Q, you need to use the dynamics where you have a Q Brownian motion here. So dV gets plugged in, the credit variation of V, square beta and square the square root, so you're going to get beta squared times V. So let me write out all this stuff. The common factor is out there. And then we get minus a prime minus b prime v. I'm being lazy now, I don't put in the t minus little t plus b, and then dv is something long. It was that thing up here. Kappa theta minus vt minus beta mu minus 1 vt, everything dt. And then there's a martingale component too. I get b here, and then the beta root vt dvtq, and I get the 1/2 b squared. Correct variation, I need to square beta, I need to square the square root, and then I need the correct variation of Brownian motion. This is dt. So because this is, yeah, so this is long and messy, right? I want the drift to be, I want the drift to be R. I want the discounted one to be 0. So if I look at the discounted one, so d of what was the martingale term? D of this one up here, e to the integral from 0 to t vu du times that mess. We will use the product rule. The first part here will come down with a minus a b. So we write it all up again. A plus b. And then times a bunch of things. So we have minus v here. And then all this stuff from before. Minus a plus b prime v dt. That was that guy. Try to collect the dt terms. This is plus a b kappa theta minus v minus beta mu minus 1 v. This was all dt. And then there was one more dt down there. 1/2 b squared beta squared vt. That's a lot of mess. And then we have the volatilities up there plus b beta root vt dbtq.
Just to clarify, right?
Yes.
A and B are functions.
Yes.
Okay. This whole, I fought for the better part of this exercise that like you're like A was like a coefficient, but yeah, it is ODEs, and then you took the derivative of A. So yeah.
Yeah, we find ODEs for A and B, right?
Yeah. I'll make sure. And when you simplified this note, we're assuming we're plugging in big T minus little
Yeah,
t.
you plug it in everywhere where you see A and B's.
Okay.
So you know that all, because this is a martingale, all this stuff here
0
is 0. So we collect terms. We're going to find VT terms. Here there's a minus a 1. Here there's a minus a b prime. Here there is a minus a b kappa. There is a minus a b beta mu minus 1. And here there is a 1/2 b squared beta squared. We want that to be 0. And then we get remaining terms. Remaining terms, so that's minus a prime plus b kappa theta. And that's equal to 0. So those are my ODs. Right, I have a b prime here, I have an a prime here.
Seems very similar to the last question on last week's homework.
But last week's homework was about pricing 0 coupon bonds. Right? So it gotta be very similar.
Did it say it was the one like with Feller's, it's like Feller's condition, something like that. That was pricing 0 coupon bond.
Yeah. Right. You were computing the same conditional expectation in a model that had the same structure as this one, this square root process. Are there any comments or questions here?
Question in the chat, I think.
There's a question in the chat. Okay, let me bring it up. there are lots of questions here. Alice is asking, why do the, so it's everything that's dt that goes to zero, that sums up to zero, right? It's all the terms. And so you can see that you have an affine function in front of dt, right? It's an affine function of bt. If I want an affine function to be zero, it has to be the constant term, and it has to be the coefficient in front of bt that must be zero. So I separate them out. I take all the constant coefficients, so that'll be the one with a prime here, the one with b kappa theta, right? D will have to add up to zero, and then all the other remaining terms that has v and has v there, it will have to add up. So here there's a minus of 1, here there's a b prime, and here there'll be minus b kappa, and so on.
And that's splitting up of the constant term and like the slope gives you the ODEs.
Yeah.
Okay.
Yeah.
I have a question about this derivation. So on the first equation on page 10, right? Can we talk about how like, or maybe like the second equation, right? Can we talk about how each of the terms in the braces was put into these forms?
I mean, this coefficient here.
That's just, yeah, that was just, yeah, I got that one. Yeah, I got that one. But
this dv, this is you have your b out here, right? So dv has drift and it has volatility. Right, so this dv here, that's the drift and that's the volatility.
let me check the.
And then the gradation, this is the last part down here. Ibrahim, you are asking, the cross variation is 0. Yes, between these two, the cross variation is 0 because the first part has just a du term. Right, so there's no cross variation between these two because the first one is smooth. There's no Brownian motion.
Oh, no, I was asking much earlier. I was just confirming, and then you answered it along the way.
Yeah, I'm sorry. These chat messages, they did not pop up. So let me.
No worries.
I apologize. There's a question that goes back to. Yeah, these go way back. So let me straighten these out before. There's a question about B and W being Markov. So I think actually Ibrahim did that in the very beginning. We proved that BT was Markov. And then the way that you prove that BT is Markov is you look at F of say BT. You write this as F of BT minus BS plus BS. Right, and then when you condition on BS,
Wait, this is proving a martingale or Markov?
Markov. Right. The question is, why is B Markov, right? And that's because now you can use the independence lemma. This part here is independent of that one. So we talked about that. That's been a while, but that's how you see that BT is a Markov process. Then there's a question about these functions of S and T. So let's go over that again. So again, the volatility coefficients here, if you write dB, right, dB is equal to dB, right? So the volatility here, this is constant equal to 1. So that's another way to see it if you want to use the same as down here, right? The function f of x constant equal to 1, this is a function of bt. So yeah, you can use the same as down here. The question is, if you test for st, is testing the st function, so you have to do both of them. For st here, if you want to answer whether or not ST by itself is Markov, you have to, the way to do it is to look at the drift and the volatility. So there will be these two here. Are the functions just of S, or is there something else that you need to keep track of? And the answer is, well, you also have to keep track of V. So S by itself is insufficient because you have both S and VT here. So if you were allowed to write these two objects here as functions of both S and V, so you're looking at the pair now, you're looking at the pair V and S, then you check, are the drift and the volatilities of these two processes just functions of V and S? And if the answer is yes, then you're Markovian. And so that's what we do here.
So
Yep, go ahead.
on the final, are we going to be replicating similarly difficult questions in front of you, like the ones we just did?
But this one here is from this final sheet.
Yeah, no, I'm just saying, like we're just going to be doing something similar to this whole process that just happened. I guess like in terms of expectation is what I mean.
I mean, so we spend now an hour and what? An hour and a half doing the first 4 or 5 parts, right? So there's no way that we can get through this in a 20-minute all exam. But I would like, for example, I would like to know if you could figure out, if I give you a stochastic process, would this be Markovian or not? So if I would give you a stochastic process, tell me, how would you figure out if this is Markovian or not? And so then you go through something like this. If I was asking you, can you compute what the PDE is that H here should satisfy, what H should satisfy down here? I mean, here you have two martingales, right? So you apply Ethos lemma, you'll figure out what the PDE is. And here you need the two-dimensional Ethos lemma to do it. Here you need the one-dimensional Ethos lemma to do it. And I would expect you to know how to apply Ethos lemma. So it got elaborate here in the end, because what we need is not expectations on the P, but we need expectations on the Q. So then we need to redo what we did, but under this measure we found in an earlier exercise, because you have an expectation here on the Q. So if you have that, then you need the Q dynamics of the processes in question. It's not enough to know what the P dynamics are. And so then it got out into this calculation that, as somebody pointed out, was very similar to what we had in the homework. Then there's a question about if we should review the midterm questions. I mean, the starting point for the final is going to be one of these questions that are on the final sheets. And then depending on how it goes, I will ask you other questions just like last time. And I claim that it's impossible to do this on the material here without having mastered the material that we had in the beginning. If you look at a slide like we had 4, no, earlier 5, right. Stuff like this. This is expressions like this one was something that we had in the already in the first midterm. So to get this right, you need to go, and so this is a bit fussy what this means. Why is this a probability measure? Then you would have to go back and review the midterm questions. So there were students that, I don't know, maybe the expectations are not set right, but it is not going to be the case that when you start solving a question on the exam one, I'm not looking for people trying to memorize my solutions and just writing them down in 20 minutes. This is not what I'm looking for. I don't mind students make mistakes and so on. It's much more important to have some understanding of why the various things fit the way that they do. Like, why did we go through, for example, if you were to start computing, start doing this last problem here, ending up in a discussion like this one, this comes up a lot. Like, why are we not just making this a martingale? Like, why are we not just saying that this should be a martingale? Well, the problem is that it's not a martingale. This is a traded security. And if it's a traded security, it's going to have drift equal to the interest rate. Equivalently, it's going to have that when you discount it, the drift is 0.
Is the drift 0 if and only if it's martingale? Is that like the same thing, or is it when it's a martingale then it has 0 drift?
Yeah. So now it's. I was hoping that nobody would ever ask that question. So I have deliberately, not been. In this course, the answer is yes. It's a martingale if and only if. If you move on into PhD studies and more advanced courses, and the answer is unfortunately no. It's not true. There is something called local martingales, and these are really not very pleasant to deal with. And unfortunately, that's in this case, the drift is equal to 0 if and only if it's a local martingale. And local martingales are very complicated to work with because they don't have constant expectation. So in this course and in the textbooks that we're using, this issue is neglected. We treat all local martingales as if they were true martingales, and this is not completely kosher. But I mean, there's no way for me to take you guys through local martingale theory. This is way too much. I feel like we're already pushing it here. Are there other questions or comments?
Just one thing. Oh, sorry. Go ahead.
On the last homework 9, there was a question asking whether the sigma algebra generated by the stock process is the same as the one generated by the 2 Brownian motions.
Yes.
Could you maybe explain that quickly?
Yep. So the answer is no. And it basically amounts to something like you have your ST, it's going to be an exponential of, say, BT plus WT. Say it's like that. Then you want to know the sigma algebra generated by S. How does it compare to the sigma algebra generated by B and W? Right, this one here is our universe. So you are not going to get anything that's bigger than that. So you always have this. Now the question is it strict? Right, so now on the right-hand side, right, imagine that you know what B and W are. If you know what B and W are, then you also know what S is. Okay, so this is why you have this inclusion. And you have it strict because if I tell you what S is, can you now tell me what B is? And can you now tell me what W is?
Not necessarily.
And that's impossible, right?
Yeah.
Like, I tell you one number. Like, well, I tell you what S is, so I could tell you what log of S is. This is equal to BT plus WT. I tell you what log of ST is. That is, I tell you what the sum is. Can you now tell me what the individual components in the sum are? And the answer is this is impossible. So you're going to get a strict inclusion here.
Is that reasoning like saying because given the information you have in the sigma algebra generated by S, you aren't able to get all the information about the sigma algebra generated in B and W?
That's right. That's right.
So is it the same thing to just make an argument based on information, or is there something? Could this sum or this function, as it were, this exponential, could it be the case that there's equality of the sets?
Yeah, I mean, no, this is not going to happen. You will not be able to back out.
So is this sum of two Brownian motions is never equal to the one generated independently by the two?
For Brownian motions that are, so keep in mind our Brownian motions, right? They have cross variation equal to 0. Right, so if I take B to be equal to W, then it's a different story. Because if I'm allowed to take arbitrary Brownian motions, then the answer to your question could be yes, right? Because if I take B to be W, then what I would get here on the right-hand side would be 2BT. Right, so if you tell me what log ST is, I can figure out what BT is. And if I tell you what BT is, of course, you can figure out what log ST is. But in the problem, in the assignment, right, the two Brownian motions, you cannot have B and W be the same. They are independent.
Cross variation is 0 when the Brownian motions are independent.
That's right. That's right.
But it might not be 0 if there's some dependence between.
Right. For example, with the one we had before, right, we had dyt would be this rho dbt plus root 1 minus rho squared dwt. And this is also a Brownian motion. And if I look at the cross variation between B and Y, right, this here is a Brownian motion for any rho between 0 and 1. And if I look at the cross variation, I'm going to get exactly rho dt. And so when I move rho up to 1, this term here drops out.
Okay.
So if I'm allowed to put this one in up here, so then I'll have BT plus YT. Then you can see as you move rho up to 1, YT here becomes like B. So when rho is equal to 1, I'm just going to get 2B here. And then there's no difference between telling me what S is and telling me what the sum is, because the two components in the sum are the same. But this can never happen in the statement of the problem because the cross variation between B and W is given to be 0.
When you considered the cross variation between B and Y, right? The coefficient term in front of the dbt is what becomes the cross variation. It becomes, and you just change the dbt into dt.
Because this here is d of B.
Right. And then B, the cross variation of B is T.
Yeah.
Okay, I got you. Okay. Yes. Cool. Do you have office hours tomorrow?
This is the last chance tomorrow morning at 9 o'clock.
Okay. Sounds good. I guess I'll. Are you doing a little extra time after class right now?
No, I need to get a shower and
okay. I was wondering if
we're already 20 minutes past. So, but there were just questions, and I overlooked all the ones in the chat. So my apologies for that. Are there any other questions before we call it a night?
Yeah, one thing about the QA, in the thing you're pointing, the QA is equal to the integral of A was it zt times like, do you know what I'm talking about?
Not really.
I think he's talking about the probability measure being equal to the integral over the set A of z dp.
Yep.
Yeah, so I remember like in the, what was it? In the discrete case, right? We had something when we were considering the Radon-Nikodym derivative in the discrete case. We defined like z omega equals p tilde omega over p omega, right? And then when you took the sum and like the things canceled out when you multiplied it by p omega, when we take the expected value. Is that making sense, or am I not making sense?
Yeah, this is how we found the Radon-Nikodym derivative in the binomial model.
Yeah. So that made sense to me, but I'm not seeing how it's connected to this. Is it connected to this thing that we have right here?
It's not going to be this simple. You cannot have, if you start taking A here, like this is for any A in FT. So if you start doing like A is equal to the set where ET is X, now you're running into problems because these are zero sets. These are null sets. So you're not going to be able to identify the CT that easily. That's why we start by creating these CTs according to this formula. Then we use Gesandtner's theorem to identify the processes. But behind all of that is this measure that has ZT as the Radon-Nikodym derivative on FT. You need to look at these sets here. Whereas in discrete time, it was okay to look at sets where your psi n would be u, right? This is okay because that's not a null set in discrete time. But if you look at where bt is equal to x, this is a null set in continuous time.
Okay. Thank you, Professor.
All right.
Tomorrow. Good night.
Good night.
Thank you, Professor. Good night.
Good night, guys. I'll see you tomorrow.
Professor, I have a question. If I could switch my exam slot.
Yeah, just look at the ones that are available and just send me an email and then I'll switch you over.
Okay, thanks.
No problem.